Servus! And welcome to our last session today, end of the Digital RE Days this year. Next to me is Merz. Welcome.
Hello.
And my name is Doreen Schäfer. I will moderate the session and Christian will present it to you. The title of this session is Ansys Maxwell Simulations for Wireless Power Applications. Wireless coils need careful simulation to predict performance and heating. But how do FEM tools compare to real measurements? Let's find out. The stage is yours.
Thank you.
Welcome.
So, at first, I want to give you a short introduction into the program Ansys Maxwell and into the ICEPAK module, which is used for thermal simulations. Then I want to present you some simulation steps of our A10 WPC coils, and I want to show you how to simulate the inductance, the AC resistance, some field distributions, and the coupling between two coils. Then I want to show you some thermal simulations of this A10 coil, and at the end I want to make a comparison between measurements and simulations. So what is Ansys Maxwell? Ansys Maxwell is a high-performance software package that uses finite element analysis to solve electromagnetic problems. It is integrated into the so-called Ansys Elektronik desktop together with all the other Ansys tools. It solves the electromagnetic field problems by solving Maxwell's equations in a finite region of space. The geometries can be created directly inside Maxwell or imported from external CAD tools, for example, Solid Edge or SolidWorks. This presentation shows the workflow of a 3D simulation of a G-coil with Ansys Maxwell. What is this ICEPAK? ICEPAK is a computational fluid dynamics software for predicting and managing thermal performance in electronic devices. It simulates airflow, temperature, and heat transfer for electronic devices. It also can simulate the heat transfer. It can model conduction, convection, and radiation in steady state and transient. It is also integrated into the Ansys Elektronik desktop and is used by us to simulate the wireless power coils at a certain AC current flowing through the respective coil at a certain frequency. Let's first have a look at the graphical interface. So at the top you can see the menus. Then at the left side you see the project manager and the properties windows. Then the history tree and the 3D modeler where you can model your coil. At the right side you see a component library where you can find a lot of already finished designs like A10, A11 coils and so on. And at the bottom, you can see the messages and the progress of your simulation. Before we start the simulation, I just want to explain you what is this G-A10 design. So the G standard defines the so-called A10 design as a coil with an outer diameter of 43 millimeters, an inner diameter of 20.5 millimeters, a number of turns, 10 per layer with 2 layers. So these parameters we will need in our simulation as well. The Litz wire is also defined as a 1.50 millimeter diameter with 105 strands and with each single strand of 0.08 millimeter diameter. The inductance is defined as 24 microhenry with a tolerance of 10%. As a ferrite material, we can use a magnetic zinc or nickel zinc with at least 0.5 millimeter thickness. The shields should extend at least 2 millimeter beyond the outer diameter of the coil. So at first we have to create the model itself. So that means the coil. So you have different possibilities to do that. So you can import directly the coil designed from SolidWorks, for example, or you can also directly import it from the library. In this case, I just built it up by myself, and I designed one of our A10 coils, which you can find on our website, which ends with the article number 410. And it consists, as you can see, at the bottom of the ferrite plate and of these 2 layers. the first step would be to define the interface for each layer. So as you can see here, for the first and the second layer, we have to just define some cross sections. Then the first step would be to assign excitation at each interface. So you right click on interface, go to assign excitation, and then we go to coil terminal. Then, as we remember in the standard, it says it has 10 turns. So for the number of conductors, we just define 10. And we also do it for the other layer. And then in the next step, we have to define the material properties in the property window. For this, we just select the two layers. And then we go in the property window to edit. And then we choose copper. As you remember, we have a certain Litz wire. So here we can define you have to go to composition to Litz wire, and then we defined the strand number, which is 105, and the wire diameter, which is 0.08. The next step is to define the ferrite material. For this, the steps are the same. So we just select the ferrite plate, and then we go to edit. And we just choose the copper from the material library, and I just define the relative permeability of 3000. The next step would be to define the so-called region, which is the space in which the electromagnetic field is calculated. So for the region sizing, I just used a rule of thumb, which was recommended by Ansys. This rule of thumb says, okay, we have the maximum dimension, which is in our case 50 millimeters, should be the distance in x, y, and z direction. Only in the plus z direction, we have to use the second time the distance. To do that, we go in the menu to draw, and then we choose region. Then we have to choose pad individual directions and go to absolute offset, and then we define the maximum length, which is 50 millimeter for all the dimensions. Only for plus z direction, we choose 100 millimeter. As you can see here, then we have the region, and inside this space, the magnetic field is calculated. If you make this region too big, the calculation time increases significantly. If you make it too small, then your results are not accurate. So it's very important to make the region in a correct way. Then the next steps are to define different settings. For this, we go in the project manager to the right click on excitations. Then we have to define a winding, which means that the two layers are now defined as one winding. And then I just choose the type current. And because we have a stranded problem, you have to choose stranded. And then as an input current, I just defined a variable, which is in this case IN for input current. The next step would be in the parameters field. We have to just assign impedance matrix. So as you can see here, you put a right click on parameters, then choose assign, and then matrix. And you just have to activate the hook, and that's all in this area. Then the next step would be to add a so-called solution setup. For this, we go right click on analysis, go to add solution setup, and then I just choose the standard values only for the frequency. I choose 125 kilohertz, which is a typical ISM frequency, which is used often for wireless power applications. Then we are almost done. We can do a validation check. So if you go to Maxwell 3D, choose validation check, and then as you can see here, if you have everywhere green hooks, then all your settings and designs are correct. And then you can just go to analyze, and then the simulation itself is starting. So in my case, my standard laptop took about 3 minutes to make the simulation. Then after the simulation is done, we want to see our results. For this, we right click on results, and then we choose this eddy current report and go to data table. Our our parameters where we are interested are the inductance and the AC resistance. So we choose these two values, then we go to new report. And as a result, you can see here at the frequency of 125 kilohertz, the simulation gives out 23.75 microhenry, which is only a deviation of 1% compared to this 24 microhenry defined in the datasheet or in the standard. Then for the RAC, I got a result of 92 milliohm, and I confirmed this value with an LCR meter at the same frequency, and I got 96 milliohm. So in this case, the deviation between measurement and simulation is also only 4%, which is also very good. Then I'm also interested in the coupling of two coils. So in this case, I just make it very easy. So I just copied the design I created, then I just flipped it at the top of the primary coil. Then I defined the distance between the two coils by adding a moving vector, and I just called the variable Z1. So because I move it in the Z direction. Then I have to define different parameter sweep. So that means I have to define the distance steps where I want to see my results, so the coupling values. For this, we go to optimetrics, we choose add, and then we go to parametric. Then this window opens, then you have to go to add, and then you have to choose your variable which you want to sweep. And then you have to define a start and a stop value. So in this case, I started at 0 millimeters, which means that the secondary coil is directly on top of the primary coil. And at end distance, I just choose 20 millimeters, and the step size is 2 millimeters in that case. Then you just have to go to add and OK, and then your parameter sweep is defined. Then at the end, I have to make the simulation again, and then I want to see my results. So for this, you have to choose results, create a AC magnetic report, go to a rectangular plot, and then I have to choose coupling coefficient. And I have to choose the windings between them. I want to see the coupling. So as you can see here, so in this graph, you see the coupling at the y-axis and the distance at the x-axis, and you can see that the measurement and the simulation fits very well. So I have a variation of about 0.5% to about 3%. How did I make the measurement? So I put the coil at the bottom, and I just glued the same coil at the top of a variable spacer, and then I just measured the primary inductance at the primary coil. So at this coil, as you can see here, in the two conditions when the secondary coil is shorted and it's opened. And that I did for each distance step, and then I just calculated the coupling with this equation. So then I'm also interested in the magnetic fields. So for this, we have to at first design the geometry. So in my case, I just choose the XZ plane, as you can see here, because in that plane I want to see the magnetic field. And then I simulated for each of my distance values the H field. And as you can see here, the animation of the absolute value of the magnetic field between the 0 and 20 millimeters. As you can see here, the magnetic field is mainly between the two coils. So it's underneath and on top of the secondary coil, you see there is no magnetic field, which we would expect because the ferrite prevents the magnetic field to go to the top or the bottom. Then I'm also interested in a thermal simulation. For this, we have to choose the ICEPAK module, which you can also buy at Ansys. So for this, you just have to go to the project and then insert ICEPAK design. And then in your project manager, this tree is opening. And then at first step, you have to copy the model which you made in Maxwell 3D into the ICEPAK history tree. So you just copy it and paste it there. That is the first step. Then you have to define the EM loss settings. For this, you just choose your design, and then right-click on thermal, go to assign, and then EM loss. Then this window opens, and then you just have to link your 3D Maxwell design with this ICEPAK module. So you do this by activating this field, and then it's so the two designs, the Maxwell 3D design is connected with your ICEPAK module. Then the next step would be to define the so-called openings at the region. So for this, you have to choose the sides of the coil, so all sides except the bottom. You have to define the so-called openings. For that, you just choose all the different surfaces of the region. You right-click and then assign terminal, and then you go to opening, and then to EM, and then this window opens. So there you can define your ambient temperature. So that means your starting point. So in this case, I just defined 22 degrees Celsius as an ambient temperature. Then the next step would be to define a so-called temperature monitor. So I have to define where I want to simulate the temperature values. So for this, I just choose the ferrite surface, then I go to monitor, assign, then I define the phase, and then I want to simulate the temperature. Then as a next step, you have to define the mesh. So for the 3D simulations, I just used the standard mesh, which is good enough for me. But for this ICEPAK module, we need to refine this mesh a little bit. And ICEPAK is based as well on the finite volume method, and the domain is discretized into a finite set of volumes. So, and then as you can see here, I refined the meshing a little bit. Then the assignment of mesh operating levels improves the meshing near complex or banded geometry in comparison to the default meshing, which is very important in this case to get accurate values. Then we just have to add a solution setup. So here we have to just put some values. So for example, the problem type. So we want to simulate the temperature and the flow. Then we have to define what kind of flow we have. So in our case, we just have a laminar flow. And then you can choose between different radiation models. So I used the easiest one, which is called discrete ordinates, but you can also use ray tracing, but then the simulation time increases a lot. So for me, this is good enough. And then I just start the simulation. Only have to go like before to analyze all. And then after some minutes, you can see here the result. So this is the ferrite bottom, and as you can see here, directly under the turns, there is the hottest spot. So in this case, so I had a temperature of 62 degrees. That means this is 40 degrees over the ambient temperature. And this temperature I got for 5 amps amplitude value, which is 3.5 amps RMS at 125 kilohertz. And this value I also confirmed with our innovative measurement setup for measuring the AC rated current, and the measured value is 3.7 amps RMS, which is quite close to the simulated value. Here I have 3 different examples for simulated and measured AC rated current values. So for this is the example I showed you right now with the 410, the A10 design. As you can see here, we have a deviation of 5%. And with 2 other standard parts I simulated and measured, I also have even a smaller deviation of only 2%. So thanks a lot for your attention. If you have some questions, you can ask now.
Perfect.
Yeah.
Thank you very much, Christian,
Yeah.
for your enlightening presentation. Before we start with the question and answer session, let me just quickly share the handout with our audience.
Yeah.
So all of you should be able now to download the handout and review the presentation. So let's switch to our questions. First one is from Herbert. Is it also possible to import existing CID files of a WPT coil and use it for the Ansys simulation?
Yes, so if you have already a CID file, for example, you have from our webpage, for example, then you can just import it into the Ansys Maxwell desktop, and then you can use it for your simulation. You maybe only have to adapt it a little bit, maybe if the sections are overlapping or something like this, and you have to define the interfaces and so on, and all the settings, but you can use it. It's not a problem normally.
Perfect. Thank you very much for that answer. So now let's move on. There's also another one from Martin. What are all the SW packages which are needed for electromagnetic field simulation with Ansys?
So there's a software package. You can buy different modules. So there's the standard package, which is the Ansys Maxwell, but you can also buy some modules like this ICEPAK, which you have to pay to get this module as well for thermal simulations. But there are a lot of other packages. So I only use the Ansys Maxwell and the ICEPAK module.
Perfect. Thank you very much.
Yeah.
Sounds like a lot of options for you to choose. There's the next one from Danny coming in. Nice. I did it in FlexPeach some years ago. Can you also do tillet in the compoling case? Maybe this one was referring to.
Flex. I do not understand what the...
I think it was maybe
Maybe we have to send us an email, then formulate it a little bit more precisely.
We will reach out to you afterwards.
Yeah.
Maybe it was connected to a different question. So there's the next question. Can you please explain in more detail how this AC rated current value is defined and why you simulate this value? Yeah,
so if a certain current flows through the coil, it heats up to a certain value. So it heats up and then it goes to a so-called steady state. So and for each of these current values, it goes to a certain temperature. And the rated current is defined as the current where the coil heats up to 40 degrees Celsius compared to ambient temperature. So in this case, in our simulation, we had a temperature of 62 degrees Celsius, which is 40 degrees over the ambient temperature. And this is very important for the customer because all our competitors only define this value in DC. But as you know, you have an AC problem when you have a wireless power, so you have a certain frequency, and for this, the rated current, which is the maximum recommended current for the customer, is lower. And then we can provide to our customers the real value at the frequency the customer is using, not the DC value, which customer do not know. If I have, for example, 200 kilohertz, the value will be even smaller. And with our measurement setup and our simulations, he gets the exact value which he wants to know.
Perfect. Yep. That sounds like we sell something unique.
Yes.
That's great. So let's move on to the next question. A lot of them coming in. This one is from Archie. Is it able to simulate multi-coils wireless charging with the same SW package?
Yes. So for multiple coils, you only just have to adapt your design. So you can, for example, simulate one of our array coils, and then you can also simulate it. It's no problem. I have done it a lot of times in the past.
Perfect. Thank you very much. Good to know. So if you need more help, just ask Christian. So let's look at the next question from Harry. Can the ferrite back phase connect to a heatsink to conduct away heat to improve rated current?
Yes. So if you have an active cooling or if you have a heatsink, then you can even achieve a higher AC rated current value, which many of our customers did in the past as well. So it's possible. Yeah.
It's possible and seems common.
Yeah.
Good to know. Thank you very much. There are more questions coming in. I think we just did that. Can the ferrite...
That's the same.
I just... Oh. Something is going on. It's not really loading again for me. Just give me a second. Danny, I think that... I see there's a follow-up question from Danny. I will fix it. When the axes of the coils are not aligned.
Yeah, so for example, we call it a misalignment. So there's a horizontal misalignment and a vertical misalignment. So and you can also just simulate any kind of misalignments, also angular misalignment. So that's not a problem for Ansys Maxwell.
Perfect, thank you very much. So now I just have to check it quickly because I think we answered... there's one left from Herbert that we missed earlier. Do you provide this kind of simulation to your customers free of charge?
Yes, as a more than you expect value, we give this to our customers during their design for free. So if a customer, for example, wants to know when you have two different coils and he wants to know the coupling between these two coils at a certain misalignment, we can give him this information for free, and then we can also provide this model to our customer if he has Ansys Maxwell.
Perfect. We love the more than you expect part. Okay. Let's have another look. I have one more question from Giuseppe. Is it possible to simulate the RFID 13.56 MHz with the same approach?
Yes, it's exactly the same. So you only have to make your windings as I showed in the simulation. Then you just have to change the frequency at 13.56 MHz. That's all.
Perfect. Giuseppe, I hope that helps you.
Yeah.
And I saw that I think that's all. And for Jasminka, who asked a question, if this webinar will also be available as a video afterwards. Yes, it will be. We will send you the recording of the session and the link to our YouTube channel. Perfect. I think that's all with the questions.
Okay.
So thank you very much for your time. Thanks to all of you for your attention. And we hope that you enjoyed this presentation and especially the whole Digital WE event. Thank you very much for joining us.